But at the dawn of this day, I'd like you to welcome Professor Mechoulam. Professor Mechoulam comes to us from Hebrew University in Jerusalem, and he needs no further introduction from me. Thank you, sir.
Thanks, Al.
There's your clock, sir.
Thank you for inviting me. It's a pleasure to be here. To be with friends is always a pleasure, and I hope that we shall have a very pleasant meeting. Just one sentence. I enjoyed what you said, Al, but you know, for somebody coming from abroad, for a foreigner, you Americans like to whip yourself too much. After all, obviously, you have positive guys and negative guys, but let's not forget that the U.S. is paying more for legitimate cannabis research than all the other countries in the world put together. And much of what we know today on cannabis, as well as on just about every medical subject, is being paid by you, by the NIH, in my case, NIDA, and so on. So don't whip yourself too much. I mean, there is enough. There are enough bad things in every place. Certainly, I would assume in this one as well. But let's try to be in relative proportions. Well, I'm not a politician. I will be speaking on 3 topics. I thought at first I'll give a general historical introduction, but then looking 2 minutes ago at the program, I saw that the teacher is going to give a lecture just after me on holistic biochemistry over a few years, and I think that I'll skip that, just give you make a few remarks, and then go on to inflammation, which is much more important than just having a scratch. Nowadays, it seems that inflammation is being looked into in neurodegenerative diseases, in cardiac diseases, and so on. So it's a very, very central point in medicine. And then I'll speak about neuroprotection. We are talking about something, about cannabis, that has been used for several thousand years. These are one of the few very old remaining records, clay tablets, and that's why they remained around in the Middle East, because they were written on clay tablets. And the Assyrians, about 3,000, 3,500 years ago, left us those clay tablets, which they more or less mentioned what we know today, namely that the drug is one that takes away the mind, and that's the Ganzi Gunu. They named not the plant, but they named the action. They named Azalu, the same plant used for neurological diseases, and the same plant under a third name used in religious rites. So it's not that different from what we know today. Then if we skip a few thousand years, then we see that the Romans, and the Greeks actually, and the Romans knew quite a bit. And I took out something on inflammation alone. And Dioscorides, of course, is the father of most of the medicine that was used in Europe for about 2,000 years. And then if we skip another 1,000 years, or 2,000 years, then I took a few citations from literature in the UK, and they were pretty good physicians, although they didn't have much to work with. They spoke about inflammations one way or the other, and Russell Reynolds, who was a physician of Queen Victoria, and apparently gave her cannabis for her migraine. In England they call it migraine, not migraine, and he was very happy with it. But here I took only one that has to do with pain. But let's not forget that we're dealing with 19th century England. Indeed, the same Russell Reynolds writes in one of his papers, but many of my colleagues prefer cannabis. Many of my colleagues prefer Dr. Hugh's favorite and useful remedy, rhubarb steeped in wine. So it was not that widely used. In any case, for about, let's say about a century, little was known medically about cannabis on a real basis. And this is a little bit strange because morphine had been isolated from opium the early 19th century. And the reason why medicine or the medical literature on cannabis was lagged behind was because the active component couldn't be isolated, or the active components, and very little significant research can be done with mixtures that change their contents every so often. So there was little known, although some very good work was done both in the UK and in the US. In the US by several laboratories, and in the UK by Lord Todd, who got very close to finding the actual active component, but unfortunately the methods that were being used were not sufficiently developed in that time, and therefore the field remained in stagnation for quite a few years more. In the early 60s, we were able to get quite a lot of hashish from the police. You know, working in a small country, it's sometimes useful. You call the head of the police and say, hello, you remember we were together at, I don't know, somewhere. Can you give me 5 kilos of hashish? I want to do some work on it. And he called the head of my institute and said, can we depend on him? The fellow said, oh yes. I was a very, very young fellow at that time, just had come back from the Rockefeller Institute in New York doing some work on natural products. He said, sure, okay, let him come over and pick up 5 kilos of good hashish. Then it turned out that both he, the head of police, and me, we had broken just about every law the Ministry of Health was making at first, but again, they signed a letter saying, okay, don't do it again, just you should get it from us, and I've been getting him from them ever since. But in any case, we looked at the contents of cannabis, of hashish. Hashish is much more potent than marijuana. And we were able, over the next few years, to isolate about a dozen cannabis constituent. Now there are about 60 of them. Most of them, all of them actually, are based on the same type of skeleton. Those that you can see here, they have 2 parts. One part is an aromatic ring, for those of you who remember your chemistry, and a part of it is terpenes. And there are lots of variations. And all of the 60 cannabinoids, including the first 5 or 10 that we isolated, are based on the same principle. Surprisingly, only one compound turned out to be psychotropic, to cause psychotropic effects which are typical for cannabinoids. But before I go on, I want to show a few compounds, acids, cannabinoid acids, which are present in the plant more than they're present in dried marijuana or dried hashish, because they change, they decarboxylate. And they turn into THC or in cannabidiol. But these compounds, people have not looked into them. These compounds are potent anti-inflammatory agents, and they have no CNS activity, to the best of my knowledge. And nobody has looked into them since we isolated and published their structures many, many years ago. I wouldn't tell you when, don't want to look that ancient, but we published them, we looked, and so did they're anti-inflammatory. As a matter of fact, we tried to look into the literature, and it turned out that a Czech group in one of the small Czech towns in Bohemia had a mixture of these compounds in their hands in the late 40s, and were using them as an anti-inflammatory mixture for inflammations on horses. They were just putting the mixture on horses, and then the inflammation just disappeared. Nobody has looked into them since. in marijuana, they don't exist because they decarboxylate on smoking. But if people use the extract of the cannabis, then probably most of the anti-inflammatory portion, most of the anti-inflammatory activity is due to these particular acids. But the compound that we isolated, 1964, tetrahydrocannabinol, THC, has been looked into in great depth. Just a few weeks ago, I got an email from a young fellow in Hungary, I don't know him, and he wrote me, "Congratulations on the 40th anniversary of your paper in the Journal American Chemical Society on this compound, on THC." And I was kind of surprised and happy, really, and felt extremely ancient. After all, that's 60 years ago. But there has been a huge amount of work on THC, and indeed, for the next 20 years, people got to know a lot about the chemistry, a lot about the clinical effects, a lot about the biochemistry of THC. One thing was still unknown 20 years later. I mean, I'm speaking now of 1964 till the mid-80s. Nothing was known about the mechanism. How does THC act in the body? And the reason for that was a mistake in the literature, a mistake in research. I'll tell you in a few seconds about it. And therefore, people didn't know whether this compound acts on something on the body, a receptor, an enzyme, anything of that sort, or was just a very general thing. People thought that it acts like an anesthetic, like a general anesthetic acting on membranes. And even the head of pharmacology at Oxford, probably the leading pharmacologist in the world at that time, thought that it acts on membranes. Anyway, the reason for that was really a mistake. And we should always realize that mistakes do occur. For a compound to act on a specific enzyme, a specific receptor, anything that's really biologically there, it should have a very specific stereochemistry. It should be built in space in a particular way. If there are two possible kinds, one is a mirror image of the other, the two of them should not act the same way because they cannot bind. The enzymes, the receptors, all of them are built in a very specific way in space. And therefore, the other compound that will act on them has to be built so that it will be able to attach itself. The other stereoisomers will not. Well, in this case, both compounds were active, both the plus and the minus. The minus is the natural one. The plus, which we had found a way to synthesize, also was active. Well, not to the extent of the first one, but to about 20%. So people said, well, these compounds don't act on enzymes. They don't act on receptors. Who knows how they act? Well, it turned out to be just wrong because we had synthesized a compound. We knew how to do it. We saw that it was being wrongly synthesized. People were buying starting materials from commercial companies, and the starting materials were not very pure. So we really purified the compounds, prepared the stereoisomers, and found out that the stereoisomer, the mirror image of the natural product, is not active at all. Therefore, chances were that the compound is indeed acting on a receptor, an enzyme, and something. And a few years later Alan Howlett in this country was able to show that it acts on a certain enzyme, forming cyclic, working on cyclic AMP, and later to find that there is a receptor, and this receptor was later fully identified at NIH. Now, receptors are not built in our brain or anywhere in our body, of course, or animal bodies, because there is a plant out there that will produce a compound that acts on them. That just doesn't work that way. Receptors are found in our body because we produce compound that will activate those receptors, and that's why there is an equilibrium, if you wish, between action and inaction, those receptors, and that's how one of the ways our body works. So obviously we thought that there should be endogenous compounds which act on those receptors. The fact that there is a plant compound, a tetrahydrocannabinol, a THC, which acts on those receptors, It's just a quirk of nature, if you wish. Anyway, it's not because of these compounds that the receptors are there. So we worked very hard for a few years, and about 12 years ago, we were able to identify, to isolate and show the structure and start biological work on a compound we call anandamide. Ananda is a name in Sanskrit which means joy. So anandamide, and it has been thoroughly investigated in the last decade. Anandamide is one of the natural compounds which we produce and which act on these receptors and do a lot of things, a long, long list of actions. Actually, there is barely a biological system, a physiological system in our bodies in which the endogenous cannabinoids, or in short, endocannabinoids, do not participate. They are involved with a lot of other things, but they are involved in just a long, long list. Now, there is a second compound which we originally found in the periphery, the spleen. Later, other people found it in the brain. There is a third compound, and then we have another compound which seems to act on the cardiovascular system and does not act on the central nervous system. This we are going to publish shortly. So there is a large variety. The first two compounds, anandamide and 2-AG, are the most important ones. And they are found in those regions of the brain where we really should expect to see them, in the regions that have to do with movement control, with coordination, learning and memory, stress, cognitive function, etc., etc. The physiological systems and conditions affected by endocannabinoids, and this is only a partial list, and a whole list will take quite a bit more space. You can see that even this short list has quite a few actions there. Starting from appetite and feeding, we found that newly born mice, for example, that in which the cannabinoid system is blocked, do not suck. They die of hunger. They don't know they're hungry. They just don't suck, although their mother wants to give them milk. But if we de-block the blocking agent, they're very happy and go and suck. And so on, the blood pressure, blood flow, etc., down to reproduction and stress. Obviously, I cannot talk about everything here. It will take hours and days. And let's look at summary, which my good Italian friend Di Maso summarized the activity, which is really a summary. Says, well, what do the endocannabinoids do? They relax, help us eat, sleep, forget, and protect. Not remember, forget. And don't think that forgetting is less important than recalling. We should have a system to forget. Otherwise, well, if you wish, we can burst. If you go down a mall and see 1,000 faces, do you want to remember all of them? Of course not. So this is, but there are also other memories, and if I have the time, I'll speak about it. There are memories that we certainly try to forget. Otherwise, each one of us will be in a constant trauma. And this system, these compounds, help us forget. I'll say a few words about it later if I have the time. So I'm now going into the inflammation part. It all started in our lab, but of course many other labs are also working on that, by working on the production of a compound called tumor necrosis factor, TNF in short. Now, TNF is a very important compound when it is produced at times we don't need it, or in amounts that are too high for us, and they're very important. They cause inflammation. As a matter of fact, my good friend with whom we have published quite a bit, Dr. Feldman from London, he's one of the leading neurologists and people that work in this field, and he just recently got the Lasker Prize for his work in the area of TNF. He found that TNF is very much involved in a lot of inflammatory conditions. So we started work with him. In this particular case, we started without him, and later we joined forces. Now, we found that 2-AG, the endogenous compound produced by the brain, and let's not forget that those compounds produced in the brain mimic, to a large extent, what the THC does. Or let's go the other way around. THC mimics the action of the compounds found in the brain. Now, 2-AG, we found that it reduces the production of TNF. Well, we were happy to see that. I'm not going to the technical details. Somebody's interested, I'll be glad to expand later on. Then we saw that 2-AG reduces the production of reactive oxygen intermediates. Now, reactive oxygen intermediates are formed in the body in quite high amounts. We obviously need oxygen, but when we have reactive oxygen intermediates, compounds formed from the oxygen, and they are generally, not always, but causing all kinds of problems, we still need some of them at a certain amount, like many other things. There is a level that we need, and above that we have problems. Much below that we have problems. We have to be in an equilibrium. Anyway, when these reactive oxygen intermediates are formed in large amounts, we do have problems. And we see that the 2-AG, one of the endocannabinoids, reduces the formation of reactive oxygen intermediates. The blue line is what we see without the 2-AG. The black line is where we see 2-AG. Then we looked, is that something we see only in the test tube? The answer is no. We see it also in vivo, in animals. So if that is true, what about cannabidiol? Cannabidiol, does it also cause the same things? The answer is absolutely yes. Cannabidiol reduces the formation of TNF. This is the first part. It reduces the formation of nitric oxide, which is also involved, not going to details, also involved in inflammation. It's also involved into chemilucence, which is the method for looking at reactive oxygen intermediates. So that was in the test tube, and we looked in vivo whether the cannabidiol does that in the whole animal. Obviously, we cannot work with humans. That's not ethical. And we saw that this is indeed what happens. Now, just in one word, it seems that cannabidiol, like many other compounds in the body, and like the endogenous cannabinoids, acts better if some of the additional compounds that are not active join forces. We call this the entourage effect. Entourage, the French entourage. And we saw that there is an entourage effect. So chances are that in the body we have an entourage effect of 2-AG acting together with other compounds which are basically inactive. So chances are that the same thing is happening with cannabis, where we may have an entourage effect, although it has not been definitely proven. There may be an entourage effect, namely there is an active compound, but other compounds which are basically inactive enhance its activity, and I wish there were more work on it. So the next thing was, okay, if we know that cannabidiol is active in vitro, is active in the test tube in doing all these anti-inflammatory things, is it active in the case of a real disease? And we looked at the inflammation of the synovium. Well, that's the part that is usually attacked in arthritis. And these are, of course, the knees and the elbows and the synovial membrane, which is the lining of the sacs that enclose the cavities of the movable joints. They are the first to be attacked, and we know that people that have arthritis suffer mostly in the elbows, in the knees, and so on. And we could show, together with Feldman, that if you take cells from animals that have arthritis, there is a model for arthritis, and we take cells, synovial cells, from animals that do not have arthritis, there is a difference in the production of TNF. That those cells that come from synovial, from knees and elbows, from synovial animals that have arthritis, they produce more TNF. There is more inflammation, of course. But if we have given those animals that have arthritis, we have given them cannabidiol, and then take the cells from their synovium, they produce less TNF. So obviously, those cells have been affected already in the animal. So we went on from there. Feldman has two types of animals in which, I mean, he has one type of animal which he can produce two types of inflammation, of arthritis. One is the regular type of arthritis, which is also seen in humans. It goes up and down. There's a week of an attack, arthritic attack, and then it goes up and down, up and down, up and down. And there is also then another type which we can produce in animal, which goes up all the time. So we looked at these animals, and we saw that cannabidiol definitely blocks the inflammation. There is a clinical score. Again, I wouldn't go into details how this clinical score is being evaluated. There is a clinical score, and we can give the animals intraperitoneally, IP, and we see that at 5 milligrams per kilogram, the clinical score is very significantly lower than in those animals that didn't get CBD or got just the placebo. Then, surprisingly, we looked also at higher levels, and we saw that the cannabidiol acts at a certain level. If we give less than that, there is no action. If we give much more than that, we get less action. This is quite typical of all cannabinoids, both the endogenous and the real ones. And here is the chronic one. It goes up and down, up and down. But if you look at the end, after 40 days, and arthritis is a chronic disease, of course, we see that there is a very, very strong, very major difference between the controls and the animals that have got CBD. Now, this is an IP. Normally, patients will not get injections every day for their arthritis, so we tried it orally, and it worked orally in the same way. These are oral. I wouldn't go because of time. Now, we had, just switching gears a little bit, many years ago we had produced a metabolite of THC, which is an acid, and it has been found that this acid is anti-inflammatory. Many of these acids are anti-inflammatory, but unfortunately, this compound, this compound on the bottom, showed some central CNS effects, and we didn't want that. So we decided to make a compound which probably will be more active, but maybe won't have CNS effects. Unfortunately, it did. Wouldn't go to all the slides. It's the compound, the acid at the top. It also has, although it has been promoted as a compound which is a potent anti-inflammatory, which it is, a potent anti-inflammatory, it does show in our hands at least quite a strong CNS effects, and therefore we decided to make a compound out of cannabidiol, which originally doesn't have any CNS effect to speak of, so that we can use that compound. And indeed, and this is a very complicated synthesis, but on the left-hand side you can see the acid which we formed. We call it HU320, and this acid has no CNS effect to speak about. Let's see, if you look at a catalepsy, if you put an animal on a ring and it will move all the time, a mouse, but if you give a compound which causes catalepsy, it will move much less. Well, THC will cause the animal to move much less. Cannabidiol will not. And so the compound we produced did not cause any of these effects. So we looked at the activity of this compound, a derivative of cannabidiol, and for the sake of, because there isn't enough time, I will just go through these extremely fast. It does everything that cannabidiol itself does, except that it is much more potent. It reduces the production of TNF, it reduces the production of oxygen intermediates, and its effect on inflammation. This is another story. We take the paw of an animal and inject it with an inflammatory agent, and there is a inflammation of a sort. if we give either cannabidiol or this compound, which we call it HU320, it reduces the inflammation. So if we look at the clinical score of that rheumatoid arthritis I was speaking about, we see the same thing. This compound, like CBD, reduces the production of arthritis or the development of arthritis, and it is an anti-arthritic drug considerably better than cannabidiol itself. So if we look at the damage produced by these in these models of damage of joint erosions, and the numbers here amount to 100 in every case. Well, if we don't give a drug, 57% show moderate to severe degree of joint erosion. But if we give HU320 or cannabidiol, the moderate to severe erosions go down very, very significantly, and quite a bit of the animals stay normal. So, to summarize this part of my lecture, we believe that the anti-arthritic potency of cannabidiol, which is present, probably is the major component of most cannabis plants, and 320, mediated through their immunosuppressive anti-inflammatory capability, renders them as promising drugs for arthritis and other chronic inflammatory diseases. As I mentioned beginning of my talk, inflammation is very much involved in a lot of medical conditions. So chances are that they should be able to help in many other conditions, and we plan to work on quite a few of these in the next few years, and I hope that many of you will be doing the same. Many of them, that's one of the reasons why THC is not equivalent to marijuana or to hashish, is because it contains large amounts of cannabidiol. And cannabidiol, as you have just seen, has a lot of potency in inflammation. And I believe that there'll be some other talks about cannabidiol. So in the few minutes that I have left, I think I have 10 minutes more. Anyway, we'll speak about neuroprotection. We wanted to see what happens to the endocannabinoids during injury. We looked at the endogenous cannabinoids formed by the brain during brain injury. And we saw, as we thought we shall see, that the endocannabinoids, particularly 2-AG, goes up on brain injury. And the red one that you see there, after 4 hours, we get about 10 times more of the endogenous cannabinoid in the brain after brain injury in a mouse. And this could be just a reaction of the brain that has nothing to do with protection. It just everything is going there in a way that we don't want to, but maybe it's just something that the brain does in order to protect itself, or to try to protect itself from the damage. So we gave a 2-AG, and we saw that 2-AG most definitely reduces the amount of damage. One of the ways to do that is to look at the water and the edema in the brain. Person with brain damage after car accident, for example, the amount of water that goes up is considerably higher. And if it goes beyond a few percent that have increased, normally we have about 78% of water in the brain. If you ask somebody, what are you? He'll say, I'm mostly water. Well, that's true. We are mostly water. But if that amount of water goes up a little bit, from 78% to 82%, it's very, very damaging to the brain. And the neurologist here, Dr. Russo, will certainly tell you, he's a neurologist, he doesn't like his patients to have 82% of water in the brain. Not very good for the brain, definitely not. And people do all kinds of things in order to prevent that. We found that giving the endogenous cannabinoid will definitely reduce the amount of edema, the amount of water in the brain. It doesn't go down to the normal state, which is 70%, but it goes lower than what we see. So, and we also see the neurological score going down. We gave this compound to these brains to our histologist, and he found that the amount of damage that one can see histologically goes down by between 30 and 50%. You can see the white part of the brain is the one that's damaged in that particular showing, and that's to say that's the infarct volume. It goes, it's much lower in the 2AG treated mice than in the control mice. So if we block the we block the cannabinoid system, the damage goes up. If we look at the blood-brain barrier, which on brain damage has been either totally destroyed or partially destroyed, we see that the 2AG protects the brain, it protects the blood-brain barrier, which is a barrier that doesn't allow compounds from the blood to go into the brain, because the blood may contain compounds which in very low amounts may damage the brain. Well, during brain damage, this blood-brain barrier is damaged. 2AG, and possibly cannabinoids as well. People have shown that for cannabinoids as well, so have we, and protects the blood-brain barrier. So it works in several ways. Let me say something about something called NF-kappa B. We have a compound in the brain, NF-kappa B, which is there, not active normally. But if there is inflammation, there is brain damage, there is something, this compound, which is together with its inactivator, sits there and waits for its chance. Once there is something that happens, whether it's inflammation, brain damage, or so on, the block of this NF-kappa B is cut out by a variety of ways. Many people working on that very important mechanism. Then this NF-kappa B protein goes into the cells, and these cells start producing inflammatory cytokines and all kinds of compounds of that sort, and therefore the slowing down of the production and free NF-kappa B is extremely important. Now we have just recently shown that 2AG slows down the production of free NF-kappa B. That means that it will slow down the production of inflammation. That has to do with the first part of what I said, but it also has to do with protection of the brain itself, because the two things go together. So we have just sent a paper showing that NF-kappa B production is blocked by 2AG. Chances are that it is also blocked by cannabidiol, which in many respects works in parallel with that. It does not, 2AG is not effective in animals in which the cannabinoid system has been eliminated. There is a biochemical way of doing it. There is a called knockout mice. In case the animals, the system is blocked out, then the cannabinoids have no effect. So it has to go through the cannabinoid receptors, through the cannabinoid compounds. And many other people have looked into that. I see that I have to finish in a few minutes, so we'll not go through the whole literature. This is the summary of this part. I want to say a few more words. The brain injury causes damage through two main channels. One, of which I spoke, production of all kinds of compounds. I mentioned cytokines, reactive oxygen intermediates, there's some glutamate and so on. These cause neuronal cell death. If we can block that, we have neuroprotection. It also works to action of vasoconstrictors. During brain damage, there is constriction of blood vessels. We can see that the 2AG, possibly also cannabinoids, block that vasoconstriction. And this is something that has not been fully investigated. We have published something on it. A few other people have done so. So chances are that we're looking at two different pathways through which cannabinoids, and we certainly know that about the endogenous cannabinoids, they do that. And in the few more minutes that I have left is a synthetic compound in which we have been able to eliminate or not to have CNS effects of this type, but this compound causes all those effects that we just saw with 2-AG, and we call this compound HU211, called dexanabinol. And this compound is now in phase 3 clinical trials as a neuroprotective agent. It has been tested and published on about 110 patients. Now it has concluded phase 3 clinical trials with 850 patients. We're waiting for the 6 months after the end of the trial so that we can analyze the results. We sincerely hope that they will be positive. And if that is the case, then we shall have the first drug on the market which will be protective, which will help reduce the damage caused by car accident and so on. And I can view in the future, hopefully, that the same drug or a very closely related drug may be used in stroke, because the basic mechanisms are more or less the same. So maybe, just maybe, we shall have something that will reduce the damage, not just of brain damage because of trauma, car accident or whatever, but also for stroke. And we have very little to use nowadays for those compounds. I'll just jump over these things. This is the dexanabinol, which has also been shown by a German group, not associated with ours, that it works on NF-kappa B, that particular compound formed in the body which causes additional damage, in this case, by moving into cells of the brain. And these are the things that have been seen with 2-HU211. And this is that it reduces the intracranial pressure. It reduces the amount of water, of the edema that is formed, just like we saw with 2-AG. And in a neurological test, which is called the Glasgow scale, we see that there is great improvement, particularly in those severe cases. So I told my neurologist, the neurologist that works on that, look, if you have a case in which a person with a mild injury comes in, why don't you make the mild injury much stronger, and then the compound will work better? He was not very happy with it. And let me end with something that has been published by a German group and by our group. It will take another 2 minutes. Quite a bit of what we know should be forgotten, especially things that have to do with trauma. And it can be shown in mice. For example, a German group showed that if they condition an animal to trauma when they hear some kind of noise. The animal hears noise and gets a shock, hears noise and gets a shock. So he's conditioned, the animal is conditioned to the noise and to the trauma coming immediately, the shock coming immediately after the noise. So these are animals that are already conditioned. They hear the noise and they freeze because they know that the shock will come. But if a shock doesn't come, they slowly, within a few days, they slowly get out of this condition. This is what happens with all of us. Otherwise, we won't be able to survive, I suppose. But if the cannabinoid system, is destroyed, let's say we take knockout mice, this particular thing does not happen. And here you have two types of mice. The mice with the red do not forget their conditioning. They stay that way for a long, long time. They remember, they continue to remember that if there is noise, they have to freeze because there will be a shock. But those animals that have a cannabinoid system which works, then they will slowly forget, and these are the animals on the lower part. So we thought that maybe we can work with the cannabinoids. I mean, they show that the system plays. What about cannabinoids? So a good friend of mine, Dr. Parker in Canada, took animals and conditioned them to something which is very widely used in psychology, into experimental psychology, and this is called place preference. She has animals moving to one or two places. It's called a place preference. One has small holes and the other has small scratches, if you wish, and they can differentiate these two places. But when they go to the place with the small holes, they are given something they enjoy, let's say cocaine or amphetamine. They like that. So as soon as they have been conditioned to that, they always go to the place with the small holes because they know that something pleasant for them will be given. So they are conditioned. That's place preference. So if you then don't give them anything, they will still go to the place they prefer because they are already conditioned. And if we give them CBD or THC for that matter, if we give them one of these two compounds, they forget their conditioning. And here, for example, in the first two things that you see, the white one and the blue one, you see the amount of the time that these animals will go to the place they prefer, the placement they prefer, because they will get something they like. But if they get cannabidiol, they won't go there more. They will just go, 50% will go to the one place and 50% will go to the other place. And the same is for THC. We try that with cocaine, we try that with amphetamine, the same. Both cannabidiol and THC cause these animals to forget, to block their conditioning. Now, is that important? I think it is very important. We have diseases, we have situations in which we do not find a way to stop remembering, to forget. I'm finishing. And the reason, for example, in the post-traumatic stress disorder, people continue to remember a trauma which in most people will be forgotten after a few days, a few months, depending on the trauma, but it is ultimately forgotten. Otherwise, we won't survive. In a few people, this does not happen. They wake in the middle of the night with hallucinations and a terrible situation, and there are very few things, except psychotherapy, that will help them. So chances are that this treatment may help people with post-traumatic stress disorder. We have started a clinical trial, and I sincerely hope that we shall be able to help patients with post-traumatic stress disorder and possibly certain forms of chronic pain, possibly certain types of phobia. Well, I want to thank my group. These are two groups. We are a mixed bag. We have people from abroad. We have Jews and Arabs. We have Jews of all kinds. We have Arabs of all kinds, and we live happily together, and which is not, unfortunately, the case throughout Israel, but this is one place of sanity, and I hope that it will be infectious. And these are many of my collaborators. As I just said in a few words, maybe, that we work both in chemistry, biochemistry, pharmacology in the clinic, and this involves a lot of people, a lot of my friends. And some of them are pharmacologists, others are clinicians. And there are a lot of collaborators abroad for the specific reason that if we want to do a test, to want to perform something that is of importance, instead of us learning the techniques or learning everything these people have invested years in learning, it's much easier to go and have a coffee with him and try to collaborate. And we have found that this is one of the great pleasures of being in academia. We work with a lot of people in a lot of places, including people here in Richmond, not far away, all over the world. And I thank them and I thank you.